then staircase, foundation. Typically these are covered in our curriculum, but some of these components are not covered. Now I also wish to mention some good books, especially for the teachers. I would suggest that you should have these books in your college library. Okay, again this handout will be given to you. Now these two are international books. This particular book I mentioned last time by Professor Pillai and Menon is a very good resource material, at least for the teachers. Okay. Now composite, whenever we are talking here, it can mean different things to different industries. Here we are meaning the composite is precast member over which there is a cast in place slab. Very much common in bridge construction also. Now these are options, like we have a filigree element, over that we have a cast in place concrete. In bridge construction we can have eye girders over which a a cast in place slab, and there are different variants of these precast members. Now these are some photographs from the construction of PIIPL, from where Mr. Ajit Bhate had come, and they are going for lots of this composite type of construction. Okay, you can see that these are the shear connectors sticking out from the beams. Now why are we going for composite construction? In a value engineering, at least you have to be aware why. First of all, it saves in the formwork, it's fast track, and it is easy to connect the members and achieve continuity. Precast, typically we talk of simply supported, but you can also have continuous members, especially emulative connections are continuous members. But there is one catch in composite construction, that we need to have adequate shear connection. That means we are casting two concretes at two different times. They have to act together. Once we have adequate shear connectors, then any strain discontinuity at the interface can be ignored. Okay. Now, if I'm talking of pre-stress construction, in addition to composite, that means the pre-stressing is there for the precast members, then also there can be different stages of precasting. Typically, the precast members will be pre-tensioned. Okay. They are brought to the site, then they can be further post-tensioned. That's why analysis gets more involved. Okay. Now, whenever we have two different concretes in one section, then we need to use what is called a transformed section. That means one is, say, M50 or M60, the precast member, whereas the cast in place is, say, M30. Quite different. How do we analyze? We have to use this transformed section, which we typically learn in our second year undergraduate. Now, for pre-stress composite sections, our first thing is to do the stress checks. The first tutorial I gave you was related with the stress checks. That is a fundamental thing of pre-stress concrete. Now, in composite construction, the stress checks comes for more number of stages compared to like conventional pre-stressed. It depends on what type of composite section we are talking about, what are the stages of pre-stressing, and there is something called type of construction of composite construction. We will see that. That means you have to be, as a designer, you have to be aware that how finally it is going to be constructed. Then only you can do the stages analysis. So there will not be any teacher to ask. Please note that. Okay. Now, type of construction in precast can be broadly classified as propped construction or unpropped construction. Propped construction means this is traditionally it has been used in India that you go to these bridge construction sites, they are bringing these girders, but then these girders are being supported, they are casting the concrete. Once the topping concrete has hardened, then you release the supports or the scaffoldings you gradually remove from the center to the out. That means the weight of the top concrete is taken as a composite section. You are not designing the precast member to carry the weight of the green concrete. On the contrary, the unpropped constructions are common in places where there is labor shortage. There, we are paying the price that we will design the precast pre-stressed member to carry the green concrete before it hardens, and then after the green concrete has hardened, when it is opened up for the live load, then it acts as a composite section. That means now you are saving the price of the scaffoldings and supports, but you are over designing the precast member to take account of the weight of the green concrete. And there can be things in between. I'm not going into the details. If you look into a book of composite construction, you will see that these are broad classifications, but there is something in between. Now, whenever we analyze a flange section, first we have to also be aware of what is the effective flange width. What is meant by the effective flange width? Where we assume that the compressive stress is to be constant. And that is given in our IS 456. Now, I told on the first day that for pre-stressed concrete, whenever we are analyzing the stresses, better we draw the individual stress diagrams, at least schematically. Find out the values, make sure they make sense, and then we shall get the resultant stress diagram. Say, at transfer, first of all, we are doing, say, at transfer of the pre-stress to the precast member only, I will be having this type of stress block. Means I am applying pre-stressing at the bottom. There can be some tension in the top or may not be. Now, after I cast the flange, then what happens is the weight of the, see, this particular block will go on changing with time. This is another headache in pre-stressed concrete, that your pre-stressing force goes on changing with time. How do you analyze as a designer? You just assume some lump sum loss and go ahead with the design. And then you come back and do a refined calculation with more detailed loss estimates. That means this block will change. On top of it, you are adding the weight of the cast in place concrete if it is an unpropped construction. Okay, these are some definitions. Now, once I have schematically drawn these diagrams, then I can write the expressions of the stresses. I have picked up these expressions from the book by Lean and Burns, and very beautifully written for the students as well as for the teachers. Okay, that means once I know the stress diagrams, this is just mix and match of the different terms and try to get the stress in the precast member, at the interface, and at the top of the whole composite section. I will skip the details of it. And these are, as I said, that these things gets a bit more changed once I have different types of construction. Unpropped and propped are the two extreme cases. There can be something in between. And accordingly, we shall apply these principles to different types of construction. I am not going more into this. Okay. And we use the principle of superposition to do all these calculations. I will skip all this. This will be given in a handout so that in your leisure time you can have a look into it. Please note what something happens here is there is a stress discontinuity. We are having shear connectors to ensure there is no strain discontinuity. But if the concretes are of different grades, there will be a stress discontinuity. Okay. I'm skipping this. Okay, this is a table in a nutshell, that what moments should I consider after the casting of the top slab, what are the moments to be considered after it acts like a composite section. This depends on the way I do my composite construction. That is what this table in a nutshell means. Next, come to structural walls. See, the way the walls can be broadly classified as structural walls means it's a generic term very much loosely floating around in the community. Whenever a load has to carry the gravity load, it is a structural wall. Okay. As compared to what is called an infill wall. Infill wall means if I just, as I told on the very first day, that if I make a partition to make it into 2 auditoriums, then it becomes an infill wall. But if I make a wall at the beginning and then cast the slab, means the wall is carrying load. It becomes a load-bearing wall. Shear walls are special type of structural walls which are designed to carry lateral forces in addition to gravity loads. Okay. Infill walls are more for enclosing the space.
So do they use gypsum boards for infill walls?
Not really. Infill walls will be made up of more like Yarracone blocks, or conventional masonry bricks, or even stone blocks can be used. Gypsum boards are used for partition walls. Okay, yes. Now, the walls can be made up of different ways. We can have cast in place concrete, which is the conventional. But in this course, we have seen a lot of application of precast concrete as walls, okay, which is called wall construction or large panel type of construction. It can be also be made up of concrete masonry units. This was also mentioned on the first day. These are also precast concrete, but they come like masonry units, which are having voids where you put reinforcement bar and fill it up with concrete. Now, the load-bearing precast panels, they will follow very similar whatever provision is there in our IS 456. It is section 32. What I'm saying is, once you go back to your place, just open this code and stay familiar where these provisions are. Okay. Coming to wall-to-wall joint, this is where I'm sharing from Aparup's work, that the wall-to-wall joint can be broadly classified as a horizontal joint, that means where I'm stacking up vertically, or it can be classified as a vertical joint where I'm placing the walls next to each other. The vertical joint, in our country we typically go for wedge joints. Wedge joints means we saw this in our field trip in Preca, that we will be using these loop boxes and the loops are opened up, put a bar and grout it. If the space is large, you have to put concrete. Or you can have U-bars, or there can be some other type of inserts instead of this U-bars or loop boxes. Whereas the draw joints are made up of plates, and Professor Sri has already shown like O connectors and other type of various options. Now this is what we had seen in this is from a Timage factory, but very similar thing we saw in the Preca, that these are the boxes which come, you install them, and then you open up and make the joints. This is conventional load-bearing walls. But next we are coming to shear walls. Means now I have to also design for lateral forces. Now these shear walls are covered in code IS 13920. Okay, if you are studying seismic design, obviously you have to be aware of this code. Okay, today I am not going to teach the code, I am just making you aware that this exists. There are certain definitions of how we define a wall. Now broadly the wall can be classified in terms of their aspect ratio in elevation. If it's a tall wall, mostly in this course we have seen tall walls. There, if it is a cast in place construction, then we tend to have this type of plastic hinge formation, or if your foundation is not properly designed, there can be uplift in the foundation also. Or if the bars are not properly inserted, then there can be pull out of the bars. Whereas other types of walls which are like short or squat in the sense that the aspect ratio, the length to height is the height to length is very less. These are governed by shear deformations. Now, this type of panels are not used in conventional construction. These are typically used for some retrofitting type of works, or where an existing frame is there, you are trying to strengthen the frame and you are inserting some concrete walls. Then these are like squat shear walls. Okay, and in between, see, these are just some broad classifications. In between, we can have intermediate walls where we can have both flexural effect as well as shear effect. If I look into the plan of walls, again, there can be different types of cross sections. Conventional rectangular or with barbell, that means certain boundary elements. Then we can have flange sections, we can have core walls. Now, all these can be made up of precast. Even core walls can be made up of precast using those U connectors. Okay. Or if the U connectors are not satisfactory, you can go for more stronger connections. Another way of classifying the walls is that if it is like a monolithic, this is one type. But if wall panels are introduced within a frame, that is called a framed shear wall. And again, the behavior of this is much more difficult than this. Behavior of this depends upon the interaction between the frame and the wall. Okay. For the tall shear wall with a rectangular cross section, the annex of 13.923 gives a nice expression to calculate the flexural capacity. Okay, please be aware of it. Okay. For shear capacity of squat walls, you have to go for what is called Stratton type of modeling. Now, this is there in the, I would say more like a research paper, but Stratton type model has come to the codes also. Okay. Next, another component which we have seen very much in our factory visit as well as all the photographs we have seen is corbels. Now, what is the difference between corbels can occur in different ways. These are the type of corbels we saw in the factory. There can be corbels on both the sides. In bridge pier caps, we have this type of corbels, and smaller versions of these rectangular cross sections, these are called brackets. Okay. Now here I am covering the corbels in general. Brackets are relatively simpler. Corbel is a very large member.
Okay, sure.
It can be even like my height.
Okay, sure.
Brackets are small pieces. Okay, small depths. Okay.
Does it vary something structural reason? Is there any difference?
This one is easy to design. You can just have some reinforcement calculated very similar to this. Whereas this one, the larger it becomes,
okay,
you have to consider all the failure conditions. That's what I will quickly talk about.
Okay.
Design of corbel is much more complicated compared to bracket.
Okay.
This is what we were seeing in the factories, that these corbels are the disturbed regions in a frame. What is meant by disturbed region? Where we cannot use the conventional Bernoulli's hypothesis to start with a strain diagram. Okay, that's why we do not go for this conventional method of analysis. We go by some sort of Stratton type model. And this is a bridge pier. Walk around in any of these metro cities, you will see that we are having all these bridge piers. Now, in IS 456, section 28 covers the corbel. See, if you go, my point is that if you go to a design office, you will be asked to use the company software or some proprietary software to do the design. But that does not mean that you do not know the basic principles. Do not use those softwares blindly. As a student, please be aware of the principles so that when you use the software, you know exactly how they have been done. Because these days, there are softwares are coming from Europe and people left and right, they are using it, getting the designs done. But do you know what is the mechanics which has been modeled in that softwares? Okay. Now the definition of a corbel is, it's like a short cantilever, but it is not flexure governed, where this particular distance, the distance of the centroid of the load from the face of the column, is substantially less compared to this depth, which is called the effective depth of the corbel. Okay. Now in corbel, what are the different failure modes? This is where, to answer your question, that in brackets we will not be having this many failure modes. The first is that this particular section can just crack through. That is called sliding shear. If I do not provide adequate reinforcement, as the load will increase, if it is going towards the characteristic value and beyond, then this reinforcement start yielding. If I do not have adequate concrete strength in this region, this is the strut or action. What is meant by strut action? That's where the concentration of stresses are. Okay. Then concrete can crush here. And finally, there can be local crushing, which is called the bearing failure. That means corbel design has to address each of these failure modes. Now this is some numerical simulation one of my students had done. That you, as a student, you can study this to feel excited. That these are like some stress contours. At cracking, for a double corbel, this is the way the stress comes down. More and more it cracks, the stress gets concentrated along these narrow bands. And this is the formation of the strut action. And we are finally saying that at ultimate state, it will be governed by the strut action. To maintain the strut in position, we need tie. Okay. What is very, in a nutshell, what is the strut and tie model approach? In a strut and tie model approach, we isolate the disturbed region separately. Just calculate what are the forces coming. Okay. Next, there is some idealization of the strut. That means I am trying to visualize that this load will go down to the column here. The reinforcement will come under tension, but since the reinforcement is having a bend, I need to there will be some stress again developing here. Wherever there is a bend of a tie, some stress will develop. And finally, this load gets transferred as a moment on the column. Idealizing this, then we design the adequate amount of ties to satisfy the equilibrium of the nodes. The strut and tie model is based on an equilibrium at the limiting state. That at every node, I should satisfy equilibrium. Typically, we need to just check a few nodes to make sure we have adequate amount of steel, and also there should be adequate amount of concrete around so that local crushing is avoided. The detailing of the bars is very important. That's where you have to check the handbooks to understand the detailing. The PCI handbook gives nice sketches. Even our Indian SP34 also gives nice sketches of corbel. This is a idealized model. There are different types of nodes, and accordingly you have to, what is my objective? My objective is to find out how much steel I need. Okay, and also to make sure that I have adequate amount of concrete to carry this force. Now this is a detailing for a corbel in SP34, which can be also used in precast industry. That means today, whatever corbel reinforcement we saw in the columns in Preca, they were having this type of inbuilt reinforcement. This is the main steel. Okay. Then we also have these ties to check the sliding shear. In order to keep the ties in place, I need to have a holder bar. And there are certain specifications by which I do not have a very ill-shaped corbel to start with. My corbel should be nicely shaped so that the flow of the force is there. Also, I need to have some sort of mechanism to develop the bars right here. That is the need of a strut and tie model. That the bars should develop right at the nodes, not just at the critical section. For the critical section, we have to have this LD. Please clearly state that you have to have LD from here. Whereas on this side, it has to be welded to this embed plate. And how you do the welding, some sort of detailing are there. Okay. Coming to deep beams. Now deep beams are also quite common in precast construction. Why? In cast in place also we have, like transfer girders we can have, but in precast, the wall panels can be supported somewhere at the two ends. And whenever a panel is supported at the two ends, because you need a space below, it becomes like a deep beam. And this is a construction from PIIPL, some sort of transfer girders they have. These deep beams can come in transfer girders, outriggers, spandrel beams. Now again, IS 456 section 29 covers deep beams. Okay. And how do we define deep beams as per the Indian code? Very similar to the American Concrete Institute code, that if the span to depth ratio is less than a certain value, then we classify it as a deep beam. And we cannot use the conventional Bernoulli's hypothesis of plane sections remaining plane. Now, the behavior of a deep beam depends on what is the type of load. Are we supporting a concentrated patch load, or are we having a distributed load from a slab? It depends, is the load coming in the top, or is the load coming somewhere in between? Today when you saw that facade elements in the Infosys multi-level car parking were supported on brackets which were somewhere in the middle of a panel, you should know that we have a problem. If a load comes at the top, you mobilize the full section. But if the load coming somewhere in the middle or in the bottom, you have to be very careful. Length of the bearing has an issue, that means you have to have a sizable bearing so that we don't have local crushing. Presence of openings, this is another headache. Architects will want to have openings to run all your service ducts. And then you have to cater accordingly. And again, our code is quite silent about these openings. And hence, what is the thumb rule we typically follow? That if there is an opening, whatever reinforcement has been intercepted, just divide that in the top and bottom, and whatever vertical reinforcement is intercepted, just put it in the left and right. But this is for small openings. Whenever openings become large, you have to do an analysis. And the behavior also depends on the way you distribute the reinforcement. Now this is a strut and tie idealization, just to show you schematically that if there are 2 point loads, this is the way we can even test our specimens. These are the struts and this is the tie. If there is a single patch load, this is the strut and tie model. And this can be also simulated numerically. That means at the initiation of cracking, this is the stress contours. As we are increasing the load and at the maximum load, you can see that the stress comes almost through this closed load paths. If the length to depth is even smaller, then we have something called an arch action. Okay, arch means the stress contours follow somewhat like this. Now the SP34 gives us certain detailing for the deep beams. What is to be noted is, first of all, most of the reinforcement gets concentrated at the bottom, which is based on whatever you need for the tie. And then there will be some reinforcement if they are supported at the two ends. We need to strengthen that typically by some U bars. We are strengthening that region. And also there is distributed reinforcement throughout to maintain the integrity of the concrete. If I look some detailing in the support region, this is a cross section in plan, that this type of U bars need to be provided. If the deep beam is having some end elements, then what is the type of reinforcement to be provided? These details are there in SP34. The last topic is the tall buildings. Now in tall buildings, again there are very good references. This book is available in the Indian edition. B.S. Taranath, Bongala Taranath was of Indian origin who worked in Houston. And I would say that he was a person from the industry who took the pain to write books which are absolutely beautifully written. Okay. And now we also have the Indian code 16700, which is championed by Ms. Alpa Sheth from Mumbai, Vakil Mehta and Sheth Group. The tallest precast building in India is in Hyderabad, the Galaxy Towers. It was mentioned by Mr. Prasad yesterday, but this is this is what our precast industry is moving towards. This is, to my knowledge, this is the tallest building in the world made up of precast concrete. Now, whenever we are trying to design tallest buildings, I would vouch that you have to understand the different load resisting systems. The first is the gravity loads, that every second of the building has to resist the gravity loads. What are the components of the structural system which are transferring the load to the ground? Okay. Next, different types of floors can be there, different types of beams can be there, different types of columns, there can be inclined members, there can be walls, finally it goes to the foundations. That means we have to understand that when the architect is conceiving this type of building, I have to understand what are the components of the structural system which I have to first model in the computational model and then design.
Then what is the Raker's column?
Raker's columns are columns which are inclined. Like this you can say a Raker's column. And I said that I am picking up photographs from India only. You see the type of buildings that are coming up. Okay. This is the architects love this.
That is the inclined member.
Inclined columns.
Okay.
Raker columns are also used in like marine construction, inclined piles. Okay. It is used in different type of applications. Anything inclined means Raker.
Okay. Design is same for both inclined and straight pillars.
No, typically Rakers are used whenever you have to resist lateral loads.
Okay.
Finally you're in an analysis model, yes, you will be having an axial force and a moment. Comes out to be similar. This is a transfer slab. You can see the thickness of the slab, which is post tension, and the columns are not continuing below. That's called this transfer slab. In fact, another of my student, Najib Sharif, was involved in this transfer slab design when he first joined Vakil Mehta and Sheth. He felt excited and sent some notes to me that this is the way he's doing. In the floor diaphragms, I had mentioned this very briefly in the first lecture that whenever we are designing for earthquake force, how the floor members, especially if they are made up of precast members, yes, tall buildings are also having similar type of slabs, maybe hollow core or maybe composite, concrete on steel deck. How to make them act together, that is called the diaphragm action. Then the lateral load resisting systems, braced frames and moment resisting frames. This is the broad classification. Again, in lack of time, I will not go into this. There are lots of possibilities are there. Wall system in our country, yes, we are having now a lot of wall system. Gone are the days when we studied as students that a building is made up of beams and columns. No. Now buildings are made up of walls, just walls and slabs. Okay. And then dual system. Dual system means it's a combination of the two. You are having the frames to have a large space, and then you are having the walls for the lateral load resistance. Space truss system, diagrid system, I believe it is, in India also it is coming up. This is just a snapshot I have taken in Chennai. This is what is happening in all the major cities. Okay, Maivan type of construction, walls with openings. You can see mega braces. This was quite a nice building when it was opened in Chennai. Now, in tall buildings, a lot of emphasis goes in the modeling. I again had talked about this in the first day, that you need to have a patience to model real life buildings. Okay, it needs many man hours to get this model done. You have to select appropriate elements, okay, depending upon the identified components, beams, slabs, shear walls, foundations. And you can also do wind tunnel tests. These days, we do have good facilities in Thiruvananthapuram. RWDI has opened up a lab in Thiruvananthapuram. We also have wind tunnel facilities in IIT Kanpur and few other places. Even in Structural Engineering Research Center, Chennai, we have wind tunnel facilities. Now, I'm ending this presentation with a few pioneers of tall building who are of the origin from the Indian subcontinent. Better we should know their names to feel that in civil engineering also you can have a wonderful career. First, to talk about Dr. Fazlur Khan. He studied in Bengal Engineering College, went on to University of Illinois at Urbana-Champaign, did PhD, worked with Skidmore, Owings and Merrill. And he was the person, in his lifetime, he designed the tallest concrete building, the tallest steel building. This particular tower, the Sears Tower, which is now called the Willis Tower, as you enter this building, you see his bust. Okay. To quote Fazlur Khan, the technical man must not be lost in his own technology. He must be able to appreciate life, and life is art, drama, music, and most importantly, people. They used to talk in different plane. But whenever you're making this type of buildings, it is changing the skyscape and how it influences our, urban life. That you can discuss in that once you reach that level. Srinivasa Iyengar from College of Engineering Guindy, then Indian Institute of Science. He worked in the same place as Fazlur Khan, Skidmore Owings. In fact, they used to be called Hal and Faz. And again, in this John Hancock Tower, which is having an exposed mega braces, both, they acted like a team. You cannot say that who designed what, but he was also involved. Any of these persons, you just go into Wikipedia and you can see what they have done. I was talking about Bungal Taranath. He worked in Houston. And again, a lot of buildings he has done. And also the nice thing is, he has documented that in the form of a book. Okay, there is a book on reinforced concrete tall buildings. There's a book on steel tall buildings. Joseph Polacco, he is also from India, from Mumbai. Okay, and he was also in US. He has also done, his company has done a lot of buildings in Mumbai. And that's it. Any question? Now it is the grand finale. The grand finale is a small quiz. Okay. You can take this out.